Maybe you can start with the questions on the Slack, then you can proceed.
Okay, okay. Yes, I was just looking at the questions now. Um, uh, yeah. Okay, so I should just go through the questions in turn. Is that what you meant?
Yeah, then you can
Okay.
proceed. Okay. Do you see
Okay,
the
sure.
questions? Do you see the questions?
Yeah, yes, yes. So okay, so yes, okay. The first question. Um, so by specifying the initial conditions yourselves, does that mean you randomly do so, or are there bounding mathematical principles that like set those initial conditions? Um, so the initial conditions are set by, so I guess you say a priori information. So um, I guess in principle they are arbitrary, but it really depends on. I see that somebody's replied an answer to this, so I agree with that. The answer is that it depends on the problem you're considering. So, for example, if you're considering a dynamical problem, so you have either a single ordinary differential equation or a system of ordinary differential equations that determines how your system evolves as a function of time. In those types of problems, they're the problems that you encounter in practice are almost always initial value problems, because usually the only information that you can specify is information at the initial time, so t is equal to 0, because that's the only information you have. Um, and so yeah, in most practical applications, it's usually set by the value of y at x or t is equal to 0, or also its higher order derivatives. So y prime at t is equal to 0, y prime at t equals to 0, etc. Okay, so the second question. So the y Euler is a list of y points relating to x points that approximate the function in the ODE. Yes. Do we need to perform a regression to obtain the approximate function of y that satisfies the ODE? Um, so the regression function that should approximate. Yeah. So essentially, that's the idea of the Euler method, is that um, it iteratively obtains an approximation to the solution of that ordinary differential equation. So, um, so yeah, just to recap, you start at some x naught and some y naught, and usually this we know what this y naught is based on the boundary conditions, and then you use the y naught and x naught to determine y1 based on changing x naught to x1, which is just x naught plus this step size h. And then once you determine y1 based on this kind of truncation that I talked about, you can then iteratively obtain y2 based on knowing y1, and then obtain y3 based on knowing y2, etc. And then you just keep going. And at every point, there's going to be some kind of small numerical error that's incurred due to the fact that it's only an approximate solution. So in the plots that I gave, you can essentially you can see this difference that's due to this kind of this error that's due to this kind of numerical approximation. So yes, in the examples that I gave, the Euler method was basically approximating the function 1 over 1 minus x squared. And you ask, does the Euler and Runge-Kutta method only work with first order ODE, or does it work with second? I think there are ways to adapt the methods to work with higher order ODEs. I'm not sure if they work with arbitrary order ODEs. I think that, for example, the Runge-Kutta can be applied to second order ODEs and potentially higher, but in most problems, you encounter in practice that it's in most cases applied to first order ordinary differential equations. So yeah, okay, the next question. So it says, so there are RK1, which is Euler adjusted, then RK2, RK3, RK4, RKn, in order to be able to solve numerically nth order that are both linear and non-linear. Sorry, I meant either linear. Okay, so yeah, so just to clarify here, when I said nth order, so RK, for example, RK2, RK4, the order that I mentioned here doesn't correspond to the order of the ODE. So that's an important point to clarify, is that, so for example, RK4 doesn't mean that you're using this to solve a fourth order ODE. So that if you recall, the order of the ODE is the highest power of y, the derivative of y that appears in the expression. So in the example that I gave, we were using it to solve a first order ODE. So an ordinary differential equation where you only have the first derivative of y. But you can, in principle, use any order of, you can use RK2, RK4, et cetera, to solve this type of equation. And in principle, I think that, so these methods can be applied to, they can be applied to either linear or nonlinear equations. But so for the example that I gave, was a nonlinear equation, but it's a particular example of a nonlinear equation that can be in fact converted to a linear equation. So it's an example that does admit an analytical solution. So that's the reason that we could compare, or at least determine, kind of illustrate the accuracy of the method by comparing it to the exact solution. So bear in mind that there may be certain problems where you aren't able to solve the ODE analytically. So you're not able to necessarily benchmark the accuracy of your method for that particular problem. So I chose problems specifically that had analytical solutions. Okay, so the next question. Okay, yeah, so the answer, okay, so the next point is just an answer to that previous question. Yeah, okay, I agree with that answer. How do we convert higher order ODEs into a system of first order ODEs, and how do we solve the system of equations? Is linear algebra also used? So I'm not sure if there's a general procedure for converting any. So if you have an ODE of any order, I'm not sure you can always. I don't think you can always decompose it into first order ordinary differential equations. I mean, you could potentially, in principle, you could by just specifying new variables. So you could, for example, call. So at least for second order ODE, I know that you can rewrite this potentially in terms of two coupled first order ordinary differential equations by introducing a kind of so your equation will have, for example, the second derivative of y, the first derivative of y, and y appearing in it. And so what you can do is you could define, say, the second, you can introduce a new variable that you could call like y2, something like that, and this could be equated to, this could be equal to the first derivative of another variable y1. And then what you can do is use this to rewrite your second order ordinary differential equation into two first order ordinary differential equations that are coupled to each other. I don't think this necessarily can be generally done, but in fact, I actually look at a problem. So in this next lecture, I actually apply. So I used a numerical package of from Scipy to solve an equation, a second order ODE that can in fact be decomposed into two coupled first order ODEs. So I consider an example where you can do this. And then the next question says, what does the round function .round do? Yeah, so it just rounds the value of x to 10 decimal places. And that's just to do with the kind of, I guess you could say, floating point addition. So for example, if you add two floating point numbers in Python, they don't necessarily give you the exact corresponding result. There might be, and that's due to the fact that, you add two floating point numbers, it will give you the number with some kind of very small approximation error. And so the reason I use that NP round is because if you don't do this rounding at each step, then the value of x at each step gets incremented by a very small amount each time. And in the while loop, at the final step, your x will actually be larger than x max. So you're basically in this iterative loop, you'll overshoot the x max, and the while loop won't record the last the value of y at the last point x max. It will be missing from the list that contains like the approximated values of y. Okay, so I think that's all the questions I think that I can see in the chat. Let me go back to the slides. Okay, so everyone can see my slides, okay, still, and still hear me, I'm assuming. Okay, I'll take that as a thumbs up. Okay, so yeah, just to briefly now, so just to recap the first lecture. So what we did in the first lecture is that I introduced you to the concept of ordinary differential equations. So I gave a formal definition of an ODE, and then introduced you to the idea of homogeneous and non-homogeneous ODEs, and for then focusing on first order ordinary differential equations, what I did is I recapped some ways in which you can analytically solve certain classes of first order ODEs. So in particular, looking at ODEs which are separable, and then also looking at first order inhomogeneous ODEs. So these types of equations generally admit analytical solutions. And so what I did was then used by looking at particular examples, so the population growth example and the RC circuit example, then looked at how you can kind of analyze the analytical solutions in using, for example, matplotlib in Python, to kind of give a kind of more intuitive feel on the kind of the meaning of this kind of analytical solution. And then we went on to look at numerical methods, so in particular the Euler method and the Runge-Kutta method. And so then I applied this to some examples showing how each of these methods tends to perform in numerically approximating the solution to a first order ordinary differential equation. And essentially on this last slide, what you can see is an example of how the performance of each of these methods in approximating the solution to this first order ODE up in the top. And based on the analysis that I showed, is that we generally expect the Euler method to perform worse, and that's because the local truncation error that you incur at each step in this kind of iterative procedure that's used to construct the solution generally scales less well with the step size. So for the Euler method, it scales as the square of the step size. For the Runge-Kutta, it scales as, so for the RK2, it scales as the cube of the step size. For RK4, it scales as h to the 5, etc. So generally for the Runge-Kutta tends to perform better than the Euler method in approximating the solution to first order ODEs. And that's what this figure illustrates. Okay, so in this lecture now, what I'll do is I'll introduce you to the Python package or the Python library Scipy, and talk about how you can basically apply. So so Scipy has kind of sub packages that contain numerical routines for basically implementing these types of numerical approaches. And so thankfully for like if you're looking at a kind of a problem like this, like say for example you want to solve an ODE, thankfully you don't have to manually do this all yourself. There are numerical routines available that pretty much handle this for you. And so this is what I'll be covering in the first part of this lecture. In the second part, I'll then also go on to look at how you can treat higher order ODEs, so ODEs of second order and higher. And then I'll focus on, again, some particular examples, like in particular the damp-driven oscillator. Okay, so as I mentioned, so Scipy is like a library, a numerical library, a library in Python that is used for kind of scientific that can used for scientific computing. So the library itself contains kind of many sub packages that can be used in for different types of problems. So, for example, on the right hand side of this slide here, I've kind of tried to produce a kind of like plot that kind of is meant to kind of roughly illustrate the kind of hierarchical structure of this library. So Scipy has all these sub packages that can be used to that has like various subroutines for doing implementing certain procedures that are used in scientific computing. So, for example, there's like the linear algebra subpackage that can do things like, for example, numerically diagonalizing matrices and things like that. There's also a statistics or stats subpackage. So the one that we're going to focus on is the integrate package that contains a function that's called solve IVP. So this is the solve initial value problem, and this is one of the main ODE solver of this integrate package. And so I also, just to mention as well, that I did actually kind of very, very briefly touch on this in previous slides. So there was one example where I for the RC circuit example, I plotted the solution, the analytical solution that depended on a homogeneous term and a second inhomogeneous term that contained an integral. And so to calculate this integral, I used another function from the integrate package, which was called the quad. And so this integrate subpackage does contain other functions that generally can be used to solve or to numerically calculate integrals, or to solve also ODEs as well. So, but we mainly will be focusing on this solve IVP function. Okay, so yeah, as I said, this solve initial value problem function, as it kind of as it's kind of implied by its name, is used for solving initial value problems. So these are generally problems of this form. So okay, here I noticed, okay, there's a little bit of a typo here. This x should be a y rather than an x. So apologize for that. But so here, this function can be used to solve problems of this type. So in particular, a system of first order ordinary differential equations. So here, this kind of arrow above the y is to indicate this is a vector. So this y is a generally d-dimensional real vector containing different unknown functions y. And this, on the right-hand side, we have this function f, which is itself also a vector. And so this generally depends on this unknown vector y. So this, I'll illustrate an example of a problem where you generally, so instead of having the previous examples that we looked at, we only considered a single first order ODE. So there are other problems where you can have a system of ODEs. So rather than just having one, you can have multiple ordinary differential equations, and some of these equations may be coupled to each other. So what I mean by that is that you could have, instead of just having a single y function, you may have a y1 function, a y2 function, a y3 function, etc. And each of these equations, say, for example, the first equation for y1 may also depend on the function y2 and also for the other equation. So an example that I kind of mentioned in the very beginning of the first lecture was this related to epidemiology. So it was this kind of SIR model of kind of infectious diseases. And so this is an example of a system of ordinary differential equations that are coupled to each other. So in that case, you have three different functions which are called S, I, and R, which represent the population that's susceptible to infection, the infected population, and also the recovered population. And so this is to kind of, as I said, this is to kind of simulate how infection spreads in the population. Okay, and so if you're to kind of look more into the kind of documentation of this library, then you can visit the documentation is found here. Okay, so how do we use this integrate package in practice? So okay, what we do is we can revisit the same problem that I considered at the end of last lecture. So okay, so we have a first order ODE, which is written in this form and has this initial, so we have this boundary condition. And now what we want to do is, rather than manually using either Euler or Runge-Kutta, we want to use this solver IPE function to do this for us. And we again just want to solve it from some initial t value, t is 0, up to t max 10. And so also just to say here that, just to point out that I've changed it. Before I was calling this independent variable x, I'm now starting to call it t. That's just to kind of be consistent with the Scipy documentation. So if you look at the Scipy, if you look at the documentation for the solver IVP function, it basically it's written using this nomenclature. So the unknown function is always written as y, and the independent variable is always written as t. So this is just me trying to be consistent with the documentation. Okay, so as before, we know that this problem is analytically solvable because this ODE is separable, and so this is just the same solution that I gave on the previous slide. And so again, I kind of encourage you to check this yourself. And so now what we want to do is to, as I said, we want to use this solver function. So the way that we do this is, so here's a snippet of code that shows how to do this. So okay, so what we do is we can import this the function solve IP from the Scipy integrate in the following way. So we write from scipy.integrate, import this function. And then in a similar way to what I did previously, we define a lambda function that essentially represents what's on the right-hand side of our ODE. So that's just the same function that I wrote previously. So this is just the sine squared times by y. And again, we list a set of t values that we want to solve for. So this is contained in this NumPy, this 1D NumPy array. So this just goes from value z to 10. By default, this linspace function, there's a third argument that tells you the number of points that you want between 0 and 10. So in this case, if you just leave it as nothing, by default it sets it to 50 points. So this is essentially this t of out is a NumPy array that contains t values from 0 to 50. It has a length of 50, containing t values from from 0 to 10. Okay, and so the way that you now use this function, so we do so this solve IVP function has a number of arguments. So the first argument is just the function that represents the right hand side of this equation. So in this case, it's just this lambda function f. So this is the first argument, and then the second argument is a pair of t values that represent the initial t value, so t naught, and the maximum t value that we want to solve up to, so t max. So here I've provided this as a kind of a list of with a pair of values, and so this is just, so this t value is just taken from this array. It's just the 0th element, and then the final value is just the final t value in this array. So as I'm sure you're aware, the way that indexing works in Python is that the -1 index corresponds to the last element in that array. Okay, and so the next argument is the value for y naught. So this is basically the boundary conditions. And so this has to be input also as a and as a list. So in here, I've just passed a list that contains only a single element. So this is just the value of y naught, which here is just it's just 1. And also what you can do with this solve IVP is you can specify the type of method that you want the solver to use. So in this case, I think by default, it automatically uses RK45. So RK45 is essentially just RK is the fourth order Runge-Kutta, but it uses a slightly more sophisticated version where it also interpolates between RK4 and RK5. So, but essentially, you can just think of it as fourth order Runge-Kutta. So I should also point out that there are other methods. So if you go to the documentation, you can see that there's other methods that you can specify. So, I mean, not to go into too many details, but there are certain problems that are in which certain other types of methods that I haven't covered in this lecture, in the last lecture and in this lecture, can be used, can potentially give you a more accurate solution. But again, I won't go over this. I'll just, in the examples that I consider, I just use the Runge-Kutta method. And so this T eval here is just also the list of so is a keyword argument that you provide that just gives you the list of values, T values that you want the solver to or you want the corresponding Y values for. So in this case, it's just the it's just the array of values between 0 and 10. So here the keyword argument is T eval. So I just set this as equal to this this NumPy array. And so this, if you run this, it basically gives you it then basically solves this ODE. And so so just the thing to point out is that I believe it provides, so what it does is as an output, what it does is it provides you with the T values that you specify it to solve for. So in this case, the times that are contained in this array, and also it contains obviously the solved values of Y. And so the way that you can extract this from this so this instance of this function, or okay, so just this, essentially just this function here. The way that you can recover these is just by using. So these are stored as attributes of this function. So basically, the way that you obtain it is by if you do sol.t, this returns the corresponding T values, and if you do sol.y, this returns the corresponding Y values. And so also yeah, as I mentioned previously, the reason why I started using Y and T as my unknown function and dependent variable is because this is the default nomenclature that this solver IVP uses. So if you want it to return if for example you're using X as the variable, you would still have to do sol.t to return the corresponding X values, if that makes sense. So just to make it easier to understand, I've just used the same kind of notation that they use in the default notation they use. Okay, and just also one point to clarify is that when you do this, so if you do sol.t to return the time values, it returns what it does, it returns this, I think, as a NumPy array with this corresponding shape. So it's just so it's technically like a 0-dimensional array. And if you do sol.y, this returns the corresponding Y values, but which is generally has a different shape to the corresponding to the array containing the T values. And so if you want to convert the Y output to be the same to be of the same dimension as the same shape as these T values, you can just use this code at the bottom. And so this basically just sets the Y output to be of the same shape as the T, such that when you plot these, it won't cause any problems. So obviously, like if you try to plot this in matplotlib, if Y and T are of different dimensions, and it will produce an error. So you have to make sure these are the same. Each of these arrays has the same shape to be able to actually plot them. Okay, so so what I've also done is I've just, in the same way as I did before, is I've just plotted the solution that you obtain from this solve IVP function against the exact solution. As you can kind of see, it gives us a very good approximation using this essentially fourth order Runge-Kutta method. Okay, so this is like an example of how you can use this function to or this numerical routine to solve a single. So when we only have so our problem is essentially just a single first order ordinary differential equation. So what, as I kind of mentioned at the beginning, this can also handle systems of ODEs. So when we when we don't just have a single function y, when we have potentially more than one function y. And so this solver IVP can handle these types of situations. So so here's another example that I consider. So here we have a system of first order coupled ODEs. So these ODEs are coupled in the sense that the first derivative of y1 depends on y2, and correspondingly the first derivative of y2 depends on y1. And so so yes, in this example, what we're looking to do is use this same function to solve this system of ODEs starting from so from t0, so this is our boundary condition, up to some maximum value t max. Okay, and so just to kind of clarify that we can, I mentioned previously that this function solves problems of this type, so where we can express our ODEs in this kind of compact vector format. So the way that, if you, I mean, just to illustrate how you can do this here, is that you can basically rewrite this system of equations in the kind of vector format. So here, what we can do is we can just define a vector y, which is just a two-dimensional real vector containing y1, y2, and then our corresponding function here is also a 2D vector in this form. And so this obviously depends on the y vector in the form of y1 and y2. Okay, so how do we now apply our function to solve this system of ODEs? So what we can do is, so we again port this function in the same way. And just to also, okay, so to mention here, this K1 and K2, these are just arbitrary constants. So for this, in this example, I've just set this equal to, again, these are kind of more or less arbitrarily chosen values. So I just set K1 to be 0.1 and K2 to be 0.4. And okay, so now to solve this, what we do is we start by defining a function that essentially expresses what's on the right hand side of our ODE. So in this case, the information is contained on this side of the system of equations. And so in this problem, so in comparison, so the last problem we considered, we only have one ODE, so we just had it just depended on essentially a single, the function f just depended on a single variable x and also y. Now we have to be a bit more careful. So because we have a system of equations here, we have to now our function here is now a 2D array. So on the previous slide, I showed. So let me just go back quickly. Here, I showed that you can represent the right hand side of our system of equations in this way. And so now, in order to apply this in the solver function, what we have to do is also write a Python function that outputs essentially a 2D vector that contains what's, essentially outputs this vector. So that's what I've done here. So here dy dt is just the right hand side of our system of equations. So here this is just what, so this is a list. So this is a list with two elements. So it's essentially what's contained again on the right hand side. So also just to point out here is that an important point is that the output of this function has to be of the same dimension as the unknown function, or the unknown vector, in this case y. So here the output is two-dimensional, and so this vector y is also two-dimensional. So here this y1 is essentially y2, and y0 is y1. So these are basically just the first and second elements of a list of two elements. So it's important to point out that this y has to contain the same number of elements as this f function. Okay, so and again, so we just specify the values, the time values that we want our solver to solve, our solver to obtain the corresponding y values for. So here I just selected 300 t values between 0 and 100. And we then call the function in the same way. So we, as the first argument, we input f, in this case, which is actually, so in this case, our function f now outputs a 2D, or it outputs a list rather than just a single value. And again, the second argument specifies so it's you have to input this as a pair of values. So the first one being the initial condition. So oh, sorry, not the initial, it's the value of t at t0. So this is just 0 in this case. And then the final value, which is 100. So this is just taken from this array of values. And also the important difference here compared to the previous example is that we now have to put input y0 as also a pair of values. So each of these, so the values in this list correspond to the initial conditions attached to y1 and y2. So in this case, I haven't actually specified this in the example panel, but here I've just chosen y1 to be to have an initial value of 1, and y2 to have an initial value of 0. So again, these are just arbitrarily chosen values. But it's important to point out that the ordering here corresponds to the ordering that's specified in this function. So here, so here y0 within this function, or I should say that the value that's placed as the first element here corresponds to the initial value for y0, and the value placed here corresponds to the initial value of y1 here. So it's just to be careful with the ordering that you specify here. Okay, and so by default we use the same fourth order range cutter, and we also then provide the solver with the array of time values that we want to solve for. And so again, we can recover the y output from this function in a kind of somewhat similar way to before. So this object has a y attribute, except at this time it's so previously its output as so in the previous problem we only had one ODE. It was output as if we did sol.y, this just output our y values as essentially as a 1D array containing the same number of y values that we specified in our t eval. So we basically obtain every y value corresponding to every t value. And so here, because this is a 2D problem, now we have it outputs this now as a 2D array where each row of this array corresponds to the solution for y1 and y2. So in this case, to obtain the solution for y1, we just index the first row. So what we're doing here is we're just taking the first row that's output from the first row of the array that's output from doing sol.y, and this corresponds to our solution for y1. And then to similarly obtain the solution to y2, we just take the next row, so the second row. Okay, and then we can then plot these in the same way that I considered in the previous slide. So what we do now is, yeah, so we just we can plot these using matplotlib, and this figure shows the corresponding results. And so here with this, so here y1 starts at 1 as kind of was specified here, and y2 starts at 0. And then you can see that they kind of satisfy this kind of oscillatory behavior, or they exhibit this kind of oscillatory behavior. And eventually, they both settle so that asymptotically they both go to 0. And so this type of problem, in fact, actually, so someone asked in the chat, somebody asked previously whether it's possible to convert higher order ODEs to just a system of first order ODEs. And so there is, for a particular problem, you can actually do that. So so in physics, a kind of very commonly encountered problem is the so-called damped pendulum. So you have a pendulum that can oscillate about an equilibrium value, and it's damped by basically air resistance. And so this type of just applying Newton's second laws of motion, you can write down a second order ordinary differential equation that describes the motion of this pendulum as it's damped. And in fact, you can re-express this, you can rewrite this as a system of two coupled first order ordinary differential equations. And essentially what this system of ODEs represents is that type of system, where here K1 corresponds to the damping rate due to kind of air resistance, and K2 relates to kind of the restoring force of the pendulum due to gravity. And so in this case, Y2 corresponds to the speed of the pendulum, or equivalently its momentum, and Y1 corresponds to its position about the equilibrium value. And so kind of what this kind of plot shows is that for these values is that the pendulum starts kind of away from equilibrium, and then you release it and it kind of oscillates backwards and forwards like this until it eventually kind of settles down, as you would kind of intuitively expect, due to this kind of damping due to the air resistance. And so kind of what's also commonly done in physics is we like producing what's called phase plots. So these are kind of plots of both the position. So at least for a 1D system like this, you can plot the position versus the momentum. And so we can analyze the behavior of a dynamical system in phase space. So this isn't really necessary, but just kind of out of interest, I've included a phase plot of this system. You can see it kind of has this kind of nice spiral behavior. So, and this is kind of due to the damping. So in the equivalent, in a special case where K1 is set to 0, where basically there's no damping, what happens is that you no longer have this kind of spiral behavior. You basically produce an ellipse. So this kind of spiral is explicitly produced by the damping of this oscillator. Okay, so this is kind of like just meant to be an overview of how you can kind of apply this kind of this function from the integrate package of Scipy. Obviously, you can consider kind of many more complicated problems. So obviously, I encourage you to go to look at the documentation yourself and to kind of play around with it and see what kind of types of ODEs you can solve. And also there are kind of, so I just applied it to base examples, but there are also other kind of arguments that you can specify in this solver. So I also encourage you to kind of look at the documentation to see what other ways that you can kind of play around with this function. Okay, so that kind of ends the part of the lectures, which was about using these kind of numerical methods to solve first order ODEs. And so now for like the remainder of this lecture, I'll now start focusing on higher order ODEs and kind of mainly focusing on like analytical methods or analytical approaches that you can use to solving these types of equations. So kind of going back to the beginning, if you recall that we defined an nth order ODE in the following way. So basically, it's just a function, an arbitrary function of some independent variable x and some unknown function y, and also containing some function of its first derivatives all the way up to its nth derivatives. So here a n all the way to a1, a naught, and b are just arbitrary. We assume these to be arbitrary functions that are differentiable. And so, as I mentioned, in general, to obtain a unique solution to any nth order ODE, we have to generally specify n boundary conditions. And so, okay, what we can do is we can start by focusing on a particular type of nth order ODE. So we can look at the homogeneous case. So if you recall this inhomogeneous term, which I call B, to look at we can look at the special case where B is equal to 0. So this is the corresponding homogeneous equation. And so since this equation, if we assume this to be linear, then okay, this is I should say that this is the definition of an nth order linear ODE. And since this is linear, then the general solution to this ODE has this corresponding form. So basically, what linearity implies is that if y1 is a solution and y2 is a solution, then a linear combination of these two functions is also a solution to the ODE. So this is like an important part of linearity. And so the way that we can generally construct a solution to these types of equations is by noting the fact that these y1, y2s, etc., which we assume to be solutions to this ODE, are what are called linearly independent. So I won't really go over this, but this is just to basically say that it's not possible to basically express y1 in terms of any of these other. If we consider this to be a set of functions, then any single function in this set can't be expressed in terms of any of the other can't be expressed as a linear combination of any of the other functions in this set. But again, I won't go over this in too much detail. Okay, so let's just kind of go to the simpler example now of where we have constant coefficients. So where each of these an n-1 up to a0 don't depend on x, so they're just constants. And so one way we can go about solving these types of equations is by kind of introducing an ansatz. So we can note that, well, if we're interested in solving this, we can note that any exponential function of x, if we differentiate it, is going to return us the same function. So this kind of makes for quite a if we want to construct an ansatz, so a kind of an ansatz being a kind of a good guess for what might be a solution to this equation, we can start with a function of this form. So here a and lambda are just unknown constants at the moment. And so what we can do is if we just assume the solution to be in this form, we can just substitute it into this equation. And what this does is effectively generates another equation, which basically is written in this form. So this gives us basically an nth order polynomial. And so, as you know, from the kind of fundamental theorem of algebra, any nth order polynomial has n roots. And so we label these roots y1 up to yn. Okay, and so what you can, I won't go over too much of the details of this, but what you can do is you can, based on the kind of properties of these solutions, or I should say, based on the properties of our auxiliary equation, these solutions will have these roots to this equation. So these solutions will have a particular form. So in the case where all these roots are real, then our solution to our nth order ODE can just be expressed as a sum of these exponentials, each depending on some coefficients c and also these roots lambda. So in cases where these lambdas are real, so either they're a combination of real numbers and also complex conjugate pairs, then our solution can be written in the following way. So this is just for any two pairs of so in the case where these roots are at least, or two of these roots are complex conjugate pairs, then the corresponding terms in the solution can be rewritten in this way. And in the case where there's another example where there's another special case where all these lambda are degenerate. That's a slightly more difficult example. But so in the following, I'll mainly focus on these first two cases. Okay, so I kind of mentioned previously that an example in physics that's quite commonly encountered, in which you consider a second order ordinary differential equation, is when you consider the what's called a damped harmonic oscillator. So this arises when you consider, for example, a simple pendulum that that just oscillates about a fixed point, and this you can also include the effects of air resistance in this. So your pendulum basically exhibits kind of damped oscillations. And so basically, this is what if you apply Newton's second laws of motion, you're able to come up with a second order ODE to describe this behavior. And it's written in this way. So just again, reiterate here, x is the position of this oscillator about its equilibrium position. Here, gamma is like a constant that describes the strength of the air resistance or friction. And this omega naught squared, so this omega naught is what's called the natural frequency of the pendulum. I won't define in detail what this is, but this is just another constant. So this omega naught is just a constant. And so what we want to do is solve this equation with these initial conditions. So we want to say that the initial position of our pendulum is at x naught, and the initial, or the first derivative of x at t is equal to naught is v naught. So here, I call this v naught because this corresponds to the speed of the pendulum at t equals to 0. Okay, and so what we do is we just use this approach that I mentioned on the previous slide. So we use this kind of ansatz of this form. So we just basically substitute that into this equation. And then this then generates the corresponding auxiliary equation. And so this is written as because this is second order ODE, we come up with a quadratic equation, so a second order polynomial. And so hopefully you know how to solve these types of equations. So we can just apply the quadratic formula to basically obtain the roots to this equation. So in this case, you can obtain these roots. So these roots are given here. And what we can do is define this kind of new variable, what I call here as omega. So here omega is equal to the square root of omega naught squared minus gamma squared. And as you can see, these in general, these roots occur as kind of complex conjugate pairs. And so what we can do is kind of based on what I said, is that we can, so the general solution will be written in this form. So it's just the sum of these two exponentials, which depend on these unknown coefficients and the roots to the auxiliary equation. And just for convenience, we can just introduce a new constant that I call D1 and D2, which just combines these C constants. Again, this is just a matter of convenience. And so the general solution is written in this way. And so now with this general solution, as we did with first order ODEs, we can determine our kind of unknown integration constants by using our boundary conditions. So as I said here, we assume that the oscillator starts at some position x naught and it has a certain initial speed. And so what we do is we just substitute t is equal to 0 into this expression. And what we also do is we take its derivative and then also substitute t is equal to 0 into its derivative. And by doing so, we basically then determine what D1 and D2 are in terms of x naught and v naught. And so this is relatively straightforward to demonstrate. So this is what you obtain by doing so. So we obtain, so D1 is just x naught and D2 depends on x naught B naught, gamma, and this other constant omega that I defined. Okay, and so what we can do is we can, with this kind of general solution, we can kind of analyze certain different regimes of behavior of our pendulum. And so so there are kind of generally three regimes of interest. So there's one in which, so if you recall, this this omega here was equal to the square root of omega naught squared minus gamma squared. And so there's basically three instances where omega is either real. So this occurs in the case where omega naught is greater than gamma. And so in that case, this is called this is the so-called underdamped regime of behavior. And so in this case, when omega is real, what happens is our pendulum just undergoes kind of coherent damped oscillations. So it just kind of swings back and forth like this. It's slowly damped and then eventually settles in its equilibrium position. There's the overdamped regime of behavior. So this is where gamma is greater than omega naught. So for just again reiterate, omega is the square root of omega naught minus gamma, omega naught squared minus gamma squared. So obviously, if gamma is greater than omega naught, then this omega will now be pure imaginary. And so what we can do is we can define a new kind of constant what I call gamma, omega tilde here, which is just I times by omega tilde. And so this omega tilde is real. And so what this describes is so-called incoherent damping. So I'll illustrate what I mean by that in the next few slides. And then there's a kind of a special case in which the two roots to our auxiliary equation are degenerate. And that's the so-called critical damping case. And so that happens when when omega naught is exactly gamma. And so that's a case which requires a kind of slightly more sophisticated way of solving. So that, if I have time, then I'll also talk about this. So, okay, so as I did previously, what we can do is we can kind of analyze these analytical solutions using in Python. So what we do, as I did before, is just we want to look at how our damped harmonic oscillator behaves as a function of time. So we create an array of various time values. So here I've just defined an array, a 1D array of t values from 0 to 10 for 250 values. Specify various values of gamma. So gamma, if you recall, is just the thing that sets effectively the strength of the friction or the kind of air resistance in the pendulum example. And then I just set, so these are just set arbitrary. So I just set omega naught to be 2. So in this case, I'm examining the underdamped case. So here, this is when the underdamped behavior occurs when omega naught is greater than gamma. So here I've just made sure that omega naught is greater than each of the gamma values that I specify in this list. And here I've just set x naught to be 1 and b naught to be 0. So so the pendulum example, this corresponds to when the pendulum is kind of if the pendulum swings this kind of way, this is when the pendulum is set at the side and is initially has no speed at t is equal to 0. Okay, so we can just define a lambda function that depends on all these constants, so on gamma, capital omega, and t. And so this is just the analytical solution I gave on the previous slide. And then we can plot the solution by basically or we can plot how our solution behaves for different values of gamma by just iterating over these values by using a for loop. So for every value of gamma in this list, we just plot plot the solution. Okay, so sorry, I mentioned that I set omega naught to always be greater. Actually, there's one value of gamma here that is actually greater than omega. So this corresponds to the overdamped case, which I'll talk about just shortly. So okay, so just to then clarify here, so you in this for loop, what I've done is I made sure to be careful. So if I specify this kind of if statement. So I say, okay, if omega naught is greater than gamma, then omega is just this, has this value. If the opposite is true, so if gamma is greater than omega naught, then I now define this, then I now define it in this way. And so this is, yeah, so this is this constant here is just the omega tilde that I specified on the previous slide. And so then for each iteration, we just plot the corresponding solution. And so here you can see how the behavior of this oscillator changes when we vary gamma. So in the case where gamma is smaller, so for the smallest value of gamma, you see that you have these damped oscillations, which is kind of what you would expect. And so by increasing gamma, which corresponds to like increasing the friction or the air resistance, then you see that these oscillations are more heavily damped. So like the pendulum, if you can think about it as the pendulum swinging like this, then it reaches a smaller amplitude every time for every period of oscillation. And then in the case where gamma then exceeds omega naught, we enter in the so-called underdamping regime. And overdamping regime. So yeah, just to clarify, so underdamping happens when omega naught is greater than gamma, and you get these coherent damped oscillations. The overdamped regime, overdamped regime happens when gamma is greater than omega naught. And what's different about this regime is that you no longer have these coherent oscillations. What happens is the pendulum just kind of swings and then eventually kind of settles back into its equilibrium position. So you no longer have these oscillations. It just undergoes a kind of exponential like damping. Okay. So, this is just exactly the same example, but I've just changed the initial condition. So I specified, in this case, I specified the initial position to be at zero, and the V naught in this case, so the speed basically to be 1. And okay, this code is exactly the same. I've just changed the initial conditions. And so here, this just illustrates how the plots change when you change the initial conditions. So here, the pendulum starts at its equilibrium position, but has a non-zero speed. And then you can see it kind of undergoes a similar type of, in the underdamped regime, it undergoes similar types of damped oscillations, whereas in the overdamping regime, you get this kind of incoherent, so non-oscillatory behavior. Okay, so hopefully that's kind of good so far. So I think I'm kind of nearing I think this lecture is meant to run to 1, although I think it's likely I'm going to finish before then. This, I think I only have maybe like 6 slides or so left, but so let's see. Okay, let's see how this goes. So, okay, in the case where so I mentioned there's a special case in the previous example where the 2 roots of our auxiliary equation are equal, and in this case we have to we have to solve the problem a little bit differently. So if we just revisit the kind of the general situation, so we go back to the nth order. So when we have an nth order ODE that has constant coefficients, so an nth order homogeneous ODE, I should say, that has constant coefficients, then what we can do is we can then generate the same. So this is the same auxiliary equation that I generated before by using this ansatz. And so in the kind of special case where we have this kind of so-called k-fold degeneracy, so what that means is that, say we have n roots, there are k roots to this polynomial whereby the roots are the same. So in this, generally speaking, k is less than or equal to n. So in this case, what we have to do is we have to modify our solution in the following way. So what we have to do is we have to include a kind of an x dependence for each of the roots in this equation. So if you recall before, in the non-degenerate case, the general solution was just written as C1 e to the lambda 1x plus C2 e to the lambda 2x, etc. In this case, we have to modify the solution in this way. Again, I won't go into the details of this, but this just kind of gives a general solution when considering roots that have exhibit degeneracy. Okay, so in the case where we're dealing with the special case where we're dealing with a second order ODE with whose corresponding auxiliary equation has twofold degeneracy or just equal roots in this case, then the solution is written in this form. So this obviously corresponds to the case where k is equal to, so twofold degeneracy is where k is equal to 2. Okay, so just revisiting the previous example of the damped harmonic oscillator. So previously we looked at the underdamped and the overdamped regime. So in the regime with critical damping, where omega naught is equal to gamma, this is when we get this kind of degeneracy that appears in the roots of the auxiliary equation. So in this case, what happens is that lambda 1 and lambda 2 are just both equal to minus gamma. And so now, based on this modification that I mentioned, is that we can now write the solution down in this kind of critically damped regime in the following way. And so this represents the general solution. And so again, to determine C1 and C2, we then have to use the boundary conditions. Since it's a second order ODE, there are two boundary conditions. And so as before, we can just determine C1 and C2 in terms of the initial position of the oscillator and also its initial speed. And so, yeah, this is just, by doing so, we can just rewrite the general solution in terms of X naught and B naught. And also this other constant gamma that it corresponds to the friction. Okay, so what we can use in this kind of we can plot the solutions in this critically damped regime. So when we have degenerate roots to our auxiliary equation, and so this is just the same code as before, but I've just modified the function, the solution for X. So this is just what's given on the previous slide. And so essentially this code just does what I did before. So it just basically takes a number of gamma values, it writes them in a list, and then what we have is a for loop that iterates over these values and then just plots the solution for each of these values of gamma. And then we can again see how our behavior changes, or the behavior of our pendulum or oscillator changes when we consider kind of stronger damping rates. So in cases where the friction has a stronger effect. And so here what we have is just these plots. So you can see that we have this kind of at least long time exponential decay, but at short times you have this kind of non-exponential decay. So if we look at the exact solution, we have this almost kind of linear decay at short times, and then that kind of eventually is at long times this is dominated by like the exponential decay. Okay, so yeah, and so okay, the next slide just shows the same thing, but with just different initial conditions. So when our pendulum is initialized at its equilibrium position but has a non-zero speed, again, you get this kind of slightly interesting behavior. So you have this kind of short time behavior that's then dominated by kind of exponential decay at longer times. And also just this note here, compared to the underdamped case, obviously you don't have the appearance of these kind of coherent oscillations. Okay, I think this is. Let me just check. Okay, I think I'll skip this material because I think that I don't think I provide. Yeah, I don't provide any kind of examples for this. So I think it's probably best if I just skip the remaining last couple of slides. So yes, so with that, let me just so I realized that we're maybe finishing a little bit early, but I think we've got through so that was just slightly over an hour. So so yeah, let me just finish by just saying thank you for your attention. Hopefully that was a somewhat interesting introduction to ordinary differential equations. Obviously, if you have any questions, then please feel free to post them on the Slack channel. Are there any? I'm not sure if there are any panelists still on the Zoom. Okay, let me just go to the Slack channel then. Let me just see if there's any new questions. I can't see any new questions at the moment. So yeah, if you have any questions, just please post them.
Is there? Hi. Hi. Oh, thank you, Graeme. Thank you for the nice lecture. So for the participants, we're gonna have a guest lecture again today. So if I would appreciate it if everyone is back by 13:40 so that we can start a bit earlier, because we actually have two guest lecturers today. So yeah, if we can be back by 13:40 from lunch. And then Graeme, there is a question for you on Slack.
Sure, let me just check. Okay, so yeah, okay, I can see the question. So how do I get to, okay, I can see this has some answers to it, but let me just read it out. So it says, how do I get to see the code for the implementation of the solve IVP from Scipy integrated with the documentation only shows how to apply the function and not the underlying implementation code. Yeah, so the documentation just shows you it just provides essentially the function. So it basically tells you that the inputs to the function and the format at which these inputs what are required, like the required format of these inputs. And I think it also contains some examples. Yeah, so I'm not sure what you necessarily mean by underlying code implementation. You mean how it actually solves the equations? I guess if you really wanted, you could look at the source. Yes, the source code, but I guess this isn't really necessary to use the function. Yeah, the only things you really need to know to use it is which method to specify. So in the examples that I gave, I used the Runge cutter, the RK45. So there are also other methods that you can use that if you look at the documentation, it specifies other methods. So, okay, the next question says, following the Python code, I assume you generated the exact solution from the analytical solution. Yes. Is there code lines for the exact solution? If not, how did you generate the? So yeah, so the maybe let me just go back to the example in the slides. So for example here, so yeah, so this the line here that's just in the legend, I called it exact. So this is just the analytical solution. So this is just this analytical solution that's just given here. So I didn't include the code that I used to plot this, but that's because I didn't have enough space on the slide. But I plotted this in exactly the same. So if you look at all the other examples that I gave where I had an analytical solution, I gave code that I use to basically plot. So while for this example, I didn't give the code explicitly, you can just basically reuse this code. If you want to, if you want to basically reproduce this plot yourself, then you can just use this other code. The idea is if you want to plot the analytical solution, the principles are the same. So for example, if I go back to an analytical example, so for example, here or here, like I plotted the analytical solution just using this code. So if, for example, in the case where if you want to say, for example, use the solve IVP function and compare it to an analytical solution and plot this, you can just plot the analytical solution using, for example, like the type of code that I've given here. So hopefully that clarifies things. Okay, it says, please give us the codes you're following in your presentation. Sure, well, the Python codes that I have are all included in the slides. So the only parts of the Python code I haven't included are the ones that just generate the plots, but then there are numerous examples of this in the slides where I show how to plot analytical solutions. So the slides themselves should have all the code that you need to be able to reproduce essentially what's shown in the slide. So using, for example, the Scipy solve function. Okay, is the def function and the lambda function the same? No, but okay, I see Andrew's answered that, and his answer is probably better than mine. So I'll just say I agree with his answer. Okay, how do you get values for T-list? Which example do you mean? So let me just go back to the final example. So I'm assuming you mean, say, for example, here. So these values are just generated from this linspace function. So this is just a function from NumPy. So what this linspace function does is it just returns an array of t values between 0 and 10. So this is the initial value, this is the final value, and then this third argument just specifies the number of values that you want. So this is how I generated this T list, basically. Okay, I guess it's maybe slightly, I call this T list, but okay, I guess technically it's a NumPy array rather than a list. But I mean, you can equivalently implement this code if you instead stored these T values in a list rather than an array. Can you repeat the time when the next session starts? So I think this has been answered in the chat as well. Check the general channel. Yeah, I'm not sure what time the next session starts, so sorry. Hopefully someone else can answer this in the chat. Yeah, so